Hi, this is week 24 of AP Physics, and we're going through Unit 5, which is called Momentum. So for this lesson, we're going to go ahead and go over elastic collisions, as well as elastic collisions at two dimensions, so glancing collisions. So for our lesson objective, says students will be able to calculate the exit velocity of an object after an elastic collision in both 1 and 2 dimensions. So let's get started. What is a perfectly elastic collision? In a perfectly elastic collision is one where momentum and kinetic energy are conserved. So the formulas for it that we'll be using are both the conservation of momentum as well as conservation of kinetic energy. So here we have kinetic energy initial and final for object 1 and 2, and here final for object 1 and 2 as well. So we're going to go ahead and use both of those formulas. Another formula we'll use as well is the following. So both of those equations can be combined to give you this formula where velocity initial of the first object minus velocity initial for the second object is equal to the negative velocity final for the first object minus velocity final for the second object. So we're going to be using that formula as well. So that formula though right here is only used for perfectly elastic collisions that are head-on, not while glancing collisions. Up next we're going to go ahead and move on to example 6. In this example we ask the following question. It says, two billiard balls of identical mass move towards each other with the positive x-axis to the right. If the initial velocities of the balls are 30 centimeters per second and negative 20 centimeters per second, what are their velocities after the balls have a collision? And assume that friction and rotational energy are unimportant. Alright, so that's what we're looking at right here in this problem. So let's go ahead and start it. Alright, so we got our two billiard balls, and was going towards the right at 30 centimeters per second, that direction. The other one is going at 20 centimeters per second, and they have the negative, meaning is going towards the left hand side. Alright, so after they collide, it's a perfectly elastic collision, so all momentum is going to be conserved, all kinetic energy is going to be conserved as well. So we're going to go ahead and we can already know the answers for these are the initial velocities. For the final velocities, this one's going to go ahead and be traveling at negative 20 centimeters per second. And this one will be traveling at 30 centimeters per second to the right. Alright, so after they bounce off of each other, that's what's going to go ahead and be the final answers for this problem. Alright, so we've got the final answers. Here they are, but that's kind of intuitive. It's like, well, I know that if they collide, they're going to transfer their energy one to the other and back and forth, and therefore those should be the answers. But it's always good to go ahead and show all the work that we need to actually figure that out mathematically. Alright, so for this problem, we're going to go ahead and use the conservation of momentum first. So here's our formula, and again, as an elastic collisions, they're bouncing and going away from each other. So we'll be using our momentum, conservation of momentum formula right here. And we're going to go ahead and also need the second formula, and we're going to go ahead and combine them to figure out the final velocity for object 1 and 2. Alright, so we're going to call this one object 1 and object 2 as well. Alright, so I'm going to go ahead and begin with the conservation of momentum. So here's our formula, and we're going to go ahead and get rid of some things from it. Alright, so let me go ahead and write it down. M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Alright, so we're looking for the velocity for object 1 final and velocity for object 2 final as well. So we're looking for two things. That's why we need two formulas. Alright, one of the things that they told us in the problem was that both balls are identical to each other. They're both two billiard balls. They're identical in mass and they are identical in size as well. So we're going to go ahead and use those to say the following. M1 is equal to M2 since they are identical to each other. So now I can go ahead and start substituting values in and out. So for example, that M1, M2 right here, I'm going to substitute it and I'm going to say that's an M1 and that's an M1. Alright, now what am I going to do? Well, I can go ahead and factor out the M's from both of these. So it'll be M1, this is V1 initial plus V2 initial equals to M1 V1 final plus V2 final. Now what can I do? Notice I can divide both sides by M1 and now they're gone. So I'm going to do that, divide by m1 on both sides, and they're gone. Alright, leaving behind just this formula right here. So it's going to go ahead and be V1I plus V2 initial is equal to V1 final plus V2 final. Alright, what's next for us? We're going to go ahead and substitute the initial velocities into this formula. We're going to try to isolate one of these two variables. So let's go ahead and do that. Initial velocity of object 1, it was 30 centimeters per second, plus initial velocity of object 2 was negative 20 centimeters per second. So that's going to go ahead and give me V1 final plus V2 final. Alright, so that's going to be a negative right there. Positive times a negative is a negative. So then it's really 30 minus 20. So that gives me 10 centimeters per second. It's equal to V1F plus V2 final as well. Alright, let's go ahead and figure out V2 final. So we're going to get the V1 and move it over to this side. I want to isolate one of the variables. So we're going to end up with this 10 centimeters per second minus V1 final is equal to V2 final. Alright, so that's the first formula that we're going to go ahead and use. I'm going to go ahead and erase a lot of this because I need the board space and rewrite that formula right there at the bottom. So we have 10 centimeters per second minus V1 final. It's equal to V2 final as well. Alright, so there we have it. Next, we need a second formula. We're going to go ahead and use this formula because it's a head-on collision as well. So we can go ahead and again plug in the values for the initial and then isolate. In this case, we're going to go ahead and try to isolate the V2 as well, and then we can equal them out to each other. I'm going to go ahead and change colors for this one. Let's see if my green's working. Alright, so we have our formulas right here. We have V1 initial minus V2 initial. It's equal to negative V1 final minus V2 final. Alright, so that's our formula. We have the initial velocity for object 1 and 2, so we're going to substitute them in here. Alright, so it's going to go ahead and be 30 centimeters per second minus negative 20 centimeters per second equals, I'm going to go ahead and distribute that negative and a positive V2 final. Alright, so I distributed the negative sign. So there we have it, just to simplify a little bit more. Alright, so here we have a negative times a negative. That is a positive, so we have 30 plus 20, that gives me 50 centimeters per second. Alright, so now I'm going to isolate the V2 again, so I'm going to go ahead and move the V1 final over here to this side, and that's going to give us our second formula. So that becomes positive V1 final equals V2 final. Alright, great. So this is our second formula. Again, I'm going to erase it because I need the board space. And I'm going to rewrite it right next to my first formula. So it's going to be 50 centimeters per second plus V1 final is equal to V2 final. Alright, so now that we have that, notice that both of these equal V2, so therefore these two formulas equal each other out. So I'm going to rewrite them as such, where I'm going to get this and substitute it where the V2 final is. So now we have 10 centimeters per second minus V1 final is equal to 50 centimeters per second plus V1 final. Alright, so now we only have one variable here. So that's the whole point of using, when you have two variables, you need two formulas, and then they can go ahead and put them together, and here that's what we did, because they both equal V2 final. Alright, now I'm going to go ahead and combine like terms, so I'm going to add plus V1 final on both sides, and move the 50 over to this side. Alright, so that's going to go ahead and give me, so I'm going to subtract 50 from this side to move it over here. 10 minus 50 will give me 40 centimeters per second, negative, because I subtracted it on this side. I'm going to add V2 to the other side to combine like terms, giving 2V1, twice as many. Alright, last step, I'm going to go ahead and divide by 2 and that gives me my first answer. V1 final 40 divided by 2 is negative 20 centimeters per second, which is what we expected the answer to be originally when we started the problem. Alright, so that takes care of the first one. Now we know what V1 final is. We can go ahead and substitute it into the first or second formula. It doesn't matter which one. And that's going to go ahead and give us the answer for V2. Alright, so let's go ahead and plug it into the top formula here in red. And I'm going to go ahead and substitute V1 final, which is negative 20 here. So it'll look like this. 10 centimeters per second minus negative 20 centimeters per second is equal to V2 final. Negative times a negative is a positive, so it's really 10 plus 20. That gives me 30 centimeters per second. So that is the velocity of V2 final, which we knew that already again since we began the problem. Alright, but there's the math for how you go about solving it and showing your work. Alright, that takes care of example 6. Up next, we're going to go ahead and work on problem number 24. Here we're asked to find the final velocities of two balls if the ball with an initial velocity of V2, which is negative 20 centimeters per second, has a mass equal to 1/2 that of the ball with an initial velocity of 30 centimeters per second. Alright, so our first object is twice the size as our second object, since it said that the second object has a mass of half that of the first object. So these are their initial velocities, and we're going to make the following claim. We're going to say that m1 is equal to twice that of m2. So that is our problem. Now, again, we're looking for two things. We're looking for final velocity of object 1 and 2. So therefore, we will need two formulas. So here we go. Conservation momentum formula plus the formula for when you have a collision that is head-on. And what we're going to do is we try to isolate one of these variables, and then you isolate the same variable on the other one, and we can go ahead and combine them together so we can go ahead and solve for this problem. Alright, so let's start with here in red for the law of conservation of momentum. And for this formula, let's see, we're going to go ahead and do some substitutions first. First, we're going to say, well, m1 equals twice that of m2. So I'm going to go ahead and substitute all of that so we can get rid of all the m1s and replace them with m2s. Alright, so I'm going to go ahead and do that. So that's going to be 2m2 here, and this m1 as well also gets replaced with 2m2. Alright, now, next I can go ahead and factor out the m2s from here. So I'm going to have the following: m2, 2, v1 initial plus v2 initial equals m2, v2 vi final plus v2 final as well. Alright, now I'm going to go ahead and divide both sides by m2. So it'll cancel out, and that's it. The m2 is now gone. Left behind are the following, so let me rewrite it. It's going to be 2 v1 initial plus v2 initial equals to 2 v1 final plus v2 final as well. Alright, so now let's begin the substituting. We have the initial velocity of object 1 and 2. Here they are. So we're going to plug those in. So it's going to be 2 multiplied times 30 centimeters per second plus negative 20 centimeters per second is equal to 2 v1f plus v2f. Alright, so this is going to be 60 minus 20, that gives me a 40 centimeters per second. It's equal to 2 v1 final plus v2 final. I'm going to go ahead and move this over here to the other side to isolate the v2 final. So that's going to go ahead and give me 40 centimeters per second minus 2 v1 final. It's equal to v2 final. Alright, so we're going to leave it like that. We've isolated one of the final velocities, v2 in this case. Alright, so now we're going to do the same for this formula, where we're going to go ahead and substitute these values in and try to isolate the v2 as well. Alright, so velocity initial is going to, for object 1, it was 30 centimeters per second minus velocity initial, negative 20 centimeters per second, is equal to, I'm going to distribute the negative, V1 final plus V2 final. Alright, up next for me, I'm going to go ahead and that's a negative times a negative, that gives me a positive 50 centimeters per second. It's equal to negative V1 final plus V2 final. And again, our goal is to go ahead and isolate the V2. So I'm going to move the V1 over to this side. So we have 50 centimeters per second plus V1 final is equal to V2 final. Alright, notice this one and that, they both equal V2. So now we can go ahead and combine them together and we can go ahead and create one formula. So I'm going to go ahead and do that. I need some board space, so I'm going to go ahead and do a little bit of erasing. Alright, so now we have our formulas. Notice that they both equal V2, right? So we can then equal them out to each other. So it'll look like this, where we have 40 centimeters per second minus 2V1 final. It's equal to 50 centimeters per second plus V1 final. So you got this part of the formula, put it there, that one there, because they both equal V2 final. Alright, so now we've got that. Let's go ahead and solve for what is V1 final. Once we have it, we can go ahead and use that to go ahead and figure out what is V2 final as well. Alright, so for this one we're going to go ahead and combine like terms. I'm going to move this, that's a negative, so I'm going to go ahead and add to both sides. So it's going to end up being 3 VIF and 50, move it over here, so I'm going to subtract 50 from both sides. That's going to give me negative 10 centimeters per second. Next I'm going to go ahead and divide both sides by 3, so that's going to give me my velocity initial final. So that's going to give me negative 3.33 centimeters per second. Alright, so that takes care of our velocity initial for object 1. So it's going to have a velocity final, negative 3.33 centimeters per second. Alright, so that is a velocity final for object 1. Velocity final for object 2, object 1 here. That's what we need to go ahead and figure out next. Alright, so now we know what velocity final is for object 1. We can go ahead and plug it into one of the previous formulas and go ahead and figure it out. Alright, so we're going to go ahead and do that. Alright, one of the previous formulas was 40 centimeters per second minus 2 VI final. It's equal to velocity to final. So now that's what we're going to go ahead and try to solve for. So we're going to get this value, put it in here, and then go ahead and solve. So it's going to be 40 centimeters per second minus 2 times negative 3.33 centimeters per second is equal to velocity to final. Alright, so I go ahead and I multiply, and notice that that becomes a positive, so it's 40 centimeters per second plus, it's going to give me 6.66 centimeters per second. And what we go ahead and do now is we go ahead and add them up. So it's going to go ahead and give me, I'm going to round it up slightly to 46.7 centimeters per second. And that is our velocity for our second object, 46.7 centimeters per second. Alright, and that takes care of problem number 24. Up next, let's check out example number 7. In this problem, they ask you a block of mass M1 is equal to 1.6 kilograms, initially moving to the right at a velocity of 4 meters per second on a frictionless horizontal track. It collides with a massless spring attached to the second block, as you see in this picture right here. And the mass of M2 is 2.1 kilograms, moving to the left with a velocity of negative 2.5 meters per second. The spring constant is 600 newtons per meter. A. Determine the velocity of block 2 at the instant when block 1 is moving to the right with a velocity of 3 meters per second. Alright, so velocity, they just made contact, they haven't come to full stop either one, and the velocity for object 1 has dropped from 4 down to 3. So that's what we're looking at, and they said go ahead and figure out the velocity of our second object that is attached to the spring. Alright, for that we're going to go ahead and use the conservation of momentum. And for the conservation of momentum, that's going to go ahead and look like this. It's going to be m1 v1 plus m2 v2 initial for both, it's equal to m1v1 final plus m2v2 final. Alright, so we have the mass, we have initial velocities, and we're just going to go ahead and isolate v2. That's our goal, isolate v2. So I'm going to go ahead and move over m1 v1 final over to this side, so I'm going to subtract. So our formula will look like this now. m1 v1 initial plus m2 v2 initial minus m1 v1 final is equal to m2 v2 final. Alright, again, all we did was move the m1 v1 final over to the other side of the equal sign, so we use subtraction to do that. That's why it's negative. Next, I want the v2 final isolated, so I'm going to go ahead and divide by m2 on both sides. m2, so that's gone. Isolating my v2 final, which is what we're trying to solve for. So now let's go ahead and plug in all the values. v2 final, so let's go ahead and start with m1 v1's initial, so it's going to be 1.60 kilograms multiplied times 4 meters per second, plus m2 v2 initial, that's going to be 2.1 kilograms multiplied times negative 2.5 meters per second, minus m1 v1 final, m1 is 1.6 kilograms multiplied times velocity final, 3 meters per second, and all of it will be divided by m2, so that's going to be 2.10 kilograms. Alright, so we're going to go ahead and plug all that into a calculator to get the answer for part A. Alright, so let's see, 1.6 multiplied times 4. Now that's a negative right there, so it's going to be a subtraction, minus 2.1 multiplied times 2.5, close parentheses, minus 1.6 multiplied times 3, close parentheses. That gives you negative 3.65, and now I'm going to go ahead and divide that by 2.1, so it gives me negative 1.73 meters per second. Why negative? Because the block is still moving towards the left. It has not come to full stop. So that will be the answer for part A, negative 1.73 meters per second to the left. Alright, so that takes care of part A. In part B, they ask you find the compression of the spring at the time. Alright, so again, how much will the spring be compressed when we have that? Alright, let me go ahead and write down negative 1.73 meters per second, our answer for part A. Alright, so how much is the spring compressed? That's what we're asked to solve for. Alright, for that we're going to use conservation of mechanical energy. Alright, so conservation of mechanical energy is going to be the kinetic energy initial plus the potential energy initial. It's equal to potential energy, kinetic energy final plus potential energy of a spring final. Okay, that's an S. There we go. Alright, so now we have that. Let's go ahead and get rid of a couple of these. First of all, initially the spring is not compressed, so I can go ahead and get rid of that. Alright, but we do have kinetic energy initially and final because none of those values are zeros. So I cannot get rid of the kinetic energy. We do have it for both sides. Alright, again, what we're looking for is the compression. Now the compression is right here in the formula for potential energy of a spring. So I'm going to go ahead and move the kinetic energy over on this side and put the actual what it is. So it is 1/2 mass times velocity of object 1 initial. Okay, and actually this is, we got two objects, so it's going to be 1/2 mass times velocity of object 2 initial. Okay, so that's our kinetic energy initial. There's two objects, that's why you see it twice. And like I said, we're going to go ahead and move over the final to this side. But again, there's two objects, so it's going to look like this. 1/2 mass times velocity of object 1 final plus 1/2 mass times velocity of object 2 final. This is object 2 as well for the mass. 2 and 1. Alright, and equal potential energy of a spring, which is 1/2 K times x squared, and the x is the amount of compression in the spring, and that's what we're looking for. So that x right there. Alright, so how can we isolate this? we can go ahead and start working on it to isolate it. One of the first things I could do is go ahead and get rid of the halves. So we can multiply everything by 2, everything on the left and everything on the right. So that's going to get rid of all those halves. Alright, and then we can go ahead and divide by k and to isolate the x. Alright, so that's going to be our strategy. So once we do that, it's going to give us the following. So we're going to multiply by 2 first of all on both sides. Squeeze that in there. Alright, and that's going to get rid of all the halves. And again, I want to divide by the k afterwards, but let me go ahead and write down what we got. M2 V2 initial minus M1 V1 final minus, because the negative distributes, M2 V2 final is equal to kx squared. Alright, now I'm going to go ahead and divide by k on both sides, so I can get rid of it. And finally, I want to get rid of the square, so I'm going to do square root on both sides, and that's going to give me just x, which is a compression. So that's the formula we need to go ahead and figure out the compression of the spring. Alright, now we have our formula. I'm going to go ahead and begin to substitute all the values in. I'll leave the formula here, then I'll erase it. Alright, so let's go ahead and substitute all these values in. M1 times V1, that's going to go ahead and be 1.6 multiplied times 4. That's initial. M2 V2 initial, that's going to be 2.1 multiplied times negative 2.5. That's going to be minus M1 V1 final, 1.6 multiplied times the final, which is 3 meters per second, minus M2 V2 final, M2 it is 2.1 multiplied times the final velocity, negative 1.73. And all of this will be divided by k, which is a constant. Constant was 600 newtons per meter, and square root this whole thing, and that's what's going to go ahead and give us the x, which is the amount of compression on the spring. Alright, from here we would just go ahead and plug everything into your calculator and get the answer. Alright, so let's take it step by step. So it's going to be 1.6 times 4. It's going to give me 6.4. And you see that negative right there? I'm going to put a minus because that's going to give me a negative. 2.1 times 2.5 gives me 5.25. Now it's going to be a negative. This is going to be 1.6 times 3. It's going to give me 4.8. And negative and a negative, that's going to be a positive. 2.1 times 1.73 gives me a positive 3.63. Alright, all of this is divided by 600, and we got to get the square root of it. That's going to give us a compression on the spring. Alright, I'm going to go ahead and put together the numerator, 1.6 minus 5.25. Minus 4.8 plus 3.63 gives me negative 0.02. All of it divided by 600 gives me 0.333 times 10 to the negative 5, square root of that answer. Gives me 5.7 times 10 to the negative 3. 5.77 times 10 to the negative 3 meters. That is the compression of the spring for this problem. Alright, that takes care of example 7. Now let's take a look at part B of example 7. Here we ask to find the compression of the spring at the time after they've made contact. So when they have this velocity final, they want to know how far is that spring compressed. So to solve for that, we're going to use the law of mechanical energy, the conservation of mechanical energy. So we have the initial kinetic and potential energy equals the final potential and kinetic energy. Alright, so that will be our formula. We can go ahead and get rid of the initial potential energy of a spring because initially the spring is not compressed. So there's no compression, so that's going to be a 0. Alright, now let's go ahead and put the formula for kinetic energy initial. Now there's two objects, you're going to see it twice. So it'll look like this. It's going to be 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. It's equal to, now the kinetic energy final, 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared plus the potential energy of a spring, which is 1/2 constant times the compression final of the spring, which is actually what we're solving for. Now, one of the first things that I could see is, like, look at all those halves. We can go in and get rid of them by multiplying both the left side and the right side by 2. So we're going to do that. That gets rid of all the halves. All right, so all those halves are gone. Then immediately after that, I want to isolate the x. So I'm going to move these guys over to the other side of the equal sign. So now we're going to end up with a formula that looks like this. m1 v1 initial squared plus m2 v2 initial squared minus, because we went over to the other side, m1 v1 final squared minus m2 v2 final squared equals k xf squared. Alright, now what's up next for us? We're going to go ahead and get rid of the k by dividing both sides by k. So I'm going to go ahead and do that. Divide by k on this side and divide by k on this side. Now I'm going to go ahead and erase it since it's gone. Finally, you see that square? I want to get rid of it. So I get rid of it by having a square root. So I'm going to go ahead and square root of both sides. And that square root is going to get rid of the square, giving us just the compression final of the spring. And there's our formula. What's next for us? Just go ahead and plug in all the numbers and get the answer. Alright, so it's going to go ahead and be compression of the spring final is equal to m1 v1. So here they are. I'm going to go ahead and put 1.6 multiplied times the initial velocity of 4, square that, plus m2 v2 initial, which is 2.1 multiplied times negative 2.5. Keep in mind that that gets squared, so it's going to get rid of that negative, minus m1 v1 final, which is 3 meters per second, squared, minus, you have m2, which is 2.1, times v2, negative 1.73. Again, that is squared, so that's going to go ahead and take care of that negative. And all of it is divided by the constant, which is given to us, was 600. There we go, and we get the square root of all of it. Alright, there we have it. What's up next for us? Just go ahead and put it into our calculator. And in our calculator, we're going to go ahead and take it step by step. Let's see. I'm going to go ahead and put my answers up here. So what is the answer for each one of these? It's going to be 1.6 times 4 squared gives me 25.6 right here. And next one, 2.1 times 2.5 squared gives me 13.1, so that's plus 13.1, and minus 1.6 times 3 squared gives me 14.4, minus 2.1 times 1.73 squared gives me 6.3, all of it divided by 600. And again, we got to square root it. So our final answer now is going to go ahead and be at the numerators divided by 600 and then square root it. So it's going to be 25.6 plus 13.1 plus 14.4. I'm sorry, that's a minus. 14.4 minus 6.3. That gives me 18 even, divided by 600. 0.03, and then finally we get the square root of that. We get 0.173 meters, and that is the compression of the spring, and that is the answer for example 7, part B. In problem 25, we're asked the following question. Is it possible for both blocks to come to rest while the spring is being compressed? Alright, so now, if both of them come to rest, the final velocity is going to be 0. So we're going to change the final velocity to 0 meters per second. If, let's say, block 1 has a velocity of 0, is it possible for velocity of block 2 to also be 0? Alright, so let's go ahead and check that out. That's what they want us to know. Is that possible for them to be 0 here and a 0 there as well while the spring's being compressed? Alright, so what we're going to go ahead and do is we're going to use the law of conservation of momentum. So momentum initial is equal to momentum final for both objects. So it's going to be m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. Alright, so we want to know for v2, is it possible that the final velocity is 0 as well? If that is a 0. Alright, so let's go ahead and solve for this. One of these we can get rid of. We're going to say that velocity final of object 1 is gone since the velocity is 0 because it says it's going to come to rest. Alright, so we're going to leave that out. And now we're just going to divide both sides by m2, and that's going to go ahead and give us our formula we need to verify. Hey, when object 1 is at rest, what is the velocity of object 2? And if it comes out to be 0, then we can say yes, it is possible for both of them to be at rest when the spring is compressed. But if it comes out to a number greater than 0, then the answer will be no, it is not possible. Alright, so let's go ahead and plug in the values and solve for velocity of object 2 final. Alright, so m1 v1 is going to be 1.6 multiplied times 4 plus m2 v2. It's going to be 2.5, negative there, all of it divided by m2, which is 2.1 for the mass. Alright, and that will give us our velocity final for object number 2. Alright, plug it into the calculator, so it's going to be 1.6 times 4 plus 2.1 times negative 2.5, close parentheses, equal, give me 1.15 divided by 2.1, gives a velocity of 0.55, and this is in meters per second. So, is it possible for both of them to be 0? No, when object 1 is at 0, object 2 is at 0.55 meters per second, so the answer to this question is no, it is not possible. In problem 26, we're asked, find A, the velocity of the block 1, and B, the compression of the spring at the instant that block 2 is at rest. So now the velocity of block 2 is 0, so we want to know first part A is find the velocity of block 1 and also part B, the compression of the spring. For part 1, the velocity of object 1, we're going to go ahead and use the law of conservation of momentum. So that's what we're going to go ahead and use to get that. So it's going to be momentum initial is equal to momentum final. We know that there's two objects, so we're going to go ahead and put momentum m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. There's our formula. Now, since the final velocity for object 2 is 0, we can go ahead and cross that out, leave it out. And this is what we're looking for, the initial velocity or the final velocity of object 1. So what we're going to do is divide by the mass of object 1 here. So that way you can cross it out, leaving behind just v1 final. Alright, so there's our formula. Now let's go ahead and plug in the values. So m1 is 1.6 kilograms. v1 is positive 4 meters per second. Plus m2 is 2.1 kilograms multiplied times negative 2.5 meters per second. All of it divided by the mass of m1, which is 1.6 kilograms. And that's going to go ahead and give us v1 final. Alright, v1 final is going to be, plugged into a calculator, 1.6 multiplied times 4. And that's going to be plus 2.1 times negative 2.5, close parentheses, equals 1.15 divided by 1.6. So that gives us an answer of velocity final 0.172 meters per second. That is the velocity final of object 1. So I'm going to go ahead and put this in. It's going to be 0.72 meters per second. Alright, so now we have the velocity final of object number 1. Let's go ahead and move along to part B. In part B, they ask you to find the compression of the spring at this instance once the second object has no velocity, the final velocity is 0. Alright, so we're going to go ahead and do that, and to do that we're going to use the conservation of mechanical energy. Alright, so it's going to be E initial is equal to E final. Alright, so that's it. Mechanical energy initial is equal to mechanical energy final. And the mechanical energy here is 2. It's going to be kinetic energy from block 1 and 2 plus potential energy of a spring. So it'll look like this: kinetic energy plus potential energy of a spring initial is equal to kinetic energy final plus potential energy of a spring final. Alright, a couple of these we can go ahead and get rid of. We can go ahead and get rid of the potential energy of a spring initial, since there is no compression on the spring initially. We can go ahead and get rid of that. Alright, from here let's go ahead and start putting in the formulas for kinetic energy. Now there's two objects initially, so we're going to go ahead and put it. It's going to look like this. 1/2 mass m1 v1 initial squared plus 1/2 m2 v2 initial square. So there's their kinetic energy. On the other side, it's going to be 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared plus potential energy of a spring, which is 1/2 k times the compression final of the spring. That's what we're solving for that x. Now, of these, we can still simplify it a little bit more. One of the things we can go ahead and simplify is this one right here. Since block 2 is coming to rest, the velocity final is not there really. So that's going to be a 0. So we can go ahead and move this kinetic energy for final for object 1 over to this side. And we can also multiply everything by 2 so we can get rid of all the halves. So that'll end up looking like this: m1 v1 initial squared plus m2 v2 initial minus, this one goes over here, m1 v1 final squared equals k x final squared. Now we're going to go ahead and try to isolate the x, which is how much the spring was compressed. So we're going to divide both sides by k. So that's gone. I'm going to go ahead and erase it. And now I have the x, but it's squared, so I'm going to go ahead and square root it. So that way I can just get rid of the squared. It's giving me just x final. Now we can go ahead and plug in the values. Alright, so values we have right here. Let's go ahead and do that. So let me restart the formula over here. I'm going to substitute all these values in. It's going to be m1 v1, so it's going to be 1.6 multiplied times 4 meters per second squared plus m2 v2 is going to be 2.1 multiplied times negative 2.5 squared. That negative is going to go away because it's going to get squared, minus m1 1.6 multiplied times velocity final 0.72 squared, all of it divided by k, the constant of the spring, which was 600, and we square root it, and there we have it. Alright, from there we're going to go ahead and plug it into the calculator, and let's see what we get. We get 1.6 times 4 squared plus, open parentheses, 2.1 times 2.5 squared, close parentheses, plus 1.6 times 0.72 squared, close parentheses, and the numerator is 39.55 over a denominator of 600. Square that. So I'm going to divide it by 600. Square root of the answer. It gives us a compression of 0.2. Let's round it off to 6 meters, 0.26 meters. Alright, and that is a compression of spring, and that takes care of problem number 26. In problem 27, we're asked the following question. A small block of mass M is released from rest at the top of the curved frictionless ramp shown above. The block slides down the ramp and is moving at a speed of 3.5 VO. When it collides with a larger block of mass M2, 1M2, at rest at the bottom of the incline. The larger block moves to the right at a speed of 2 VO immediately after the collision. So here's a picture of the diagram, and here I also have a similar one right up here. So we have M begins from rest, slides down, and once it gets to the bottom of the curve, it has reached a speed of 3.5 VO, and then it'll collide with the 1.5 M block, the larger block, and that larger block should move to the right at 2 VO, and that's going to be its velocity. Now they ask you to express your answer from the following questions in terms of the given quantities. So it's going to be like, instead of VI, I should put 3.5 VO for velocity initial for our first object. And also 2 VO for velocity final for our larger object. Alright, so we're going to go ahead and do that. It says A, determine the height H for the ramp at which a small block is released. Alright, to answer that question, I'm just going to look at the small block from here to the instant before the crash. And we're going to go ahead and, again, just look at that piece of this problem from here to the instant before the crash. So to solve for the height, we're not going to look at the second object at all. So the instant before the crash is what we're looking at. Alright, where its velocity, the instant before the crash, is 3.5. So to solve for the height, it's going to be the law of conservation of mechanical energy. So we're going to look like this. So it's going to be mechanical energy initial is equal to mechanical energy final. So mechanical energy is kinetic energy plus potential energy. So that's going to look like this. It's going to look kinetic energy initial plus potential energy due to gravity initial is equal to kinetic energy final plus potential energy due to gravity final. Alright, now, again, we're only looking at the first object from here to there. And notice that at the bottom, at the end, the block is on the bottom of the ramp, so it's got no potential energy due to gravity final. And the block begins up here, so from rest, so it's got no kinetic energy initial. So there we go, that's going to be our formula for potential energy due to gravity final. It is mass times gravity times height, which is H is what we're looking for. On the other side, it's going to go ahead and be kinetic energy is 1/2 mass times velocity for object 1 final squared. Alright, so that is its final velocity. Alright, so the final velocity for this problem is actually going to be 3.5. Again, we're looking at the instant before it collides. Alright, so we're going to go ahead and plug that in there. And first of all, we can go ahead and get rid of the mass. Look at the mass on both sides. We can go ahead and get rid of that by dividing by mass on both sides. So we're going to do that. Alright, next, what am I going to do? I'm going to go ahead and divide by G on both sides. So that can cancel out as well. Alright, so that's going to give me H is really equal to V squared over G and 2 because of the half. There we go. So it's our formula. But again, they want it in their units. So G is fine, but velocity final squared, it should have been 3.5 because that was the velocity of the block the instant before it collides. Alright, so I'm going to go ahead and replace that. 3.5 VO squared 2G. Alright, so there's our formula. Could we simplify it further? Sure we could. We could leave it like that, but we're going to go ahead and take it a step further. We're going to square that 3.5 squared. Gives me 12.25 divided by 2. So simplify just a hair further. 6.125 VO squared over G. And that will be the height of the ramp. And that would go ahead and take care of part A. In part B, they ask us a follow-up question. Determine the speed of the small block after the collision. So now we're going to look at the whole thing. So we know its velocity the instant before it crashes, it was 3.5. Now they want to know what's the velocity after the collision. Alright, initially this larger block is at 0, so it's at rest, so it's VO. Alright, and this one, it's going to go ahead and be, this given to us 2 VO after the collision. Alright, so that's the velocity final. So again, we're looking for velocity initial of a smaller block. Alright, so now let's go ahead and plug it in to the formula. Which formula am I going to use? Conservation of momentum for this problem to go ahead and figure out the speed final after the collision. Alright, so momentum is going to be for two objects, m1 v1 initial plus m2 v2 initial will equal m1 v1 final plus m2 v2 final. Alright, so there we have it, and what we're looking for is this guy right there, the final velocity of our first object, the smaller of the two blocks. Alright, so we need to isolate this one. Alright, so that's going to be our goal. Alright, what can we get rid from here? Initial velocity of the larger block. Alright, so that one had an initial velocity of 0, so I'm going to go ahead and get rid of that. That we can go ahead and get rid of. This had no velocity, it was at rest, the larger block. So now, let's go ahead and work. Let's move this over to that side, so we can go ahead and isolate the V1. So M1 V1 initial minus M2 V2 final, it's equal to M1 V1 final, which is what we're looking for. Now I'm going to go ahead and divide by M1 on both sides, and that's canceled out, so giving me my formula for the final. So there you have it. Next, it's done, right? But again, if we look back, it says express your answers to the following in terms given. All right, so did they give you an M1? No, they just, M1 we're really using, it's a capital M. All right, so all those M1s I'm going to replace them with a capital M. So I'm going to do that. Capital M here. What about M2? M2 was really 1.5 M, so I'm going to replace that as well. 1.5 M. Alright, velocity 1 initial, that was given to us. Velocity 1 for object 1 initial, 3.5 VO. So I'm going to replace that. 3.5 VO. Sorry, squeezing that in there. Alright, let me rewrite it a little bit better. So there we have it. And velocity final for a second object is 2 VO. So I'm going to replace that times 2 VO. There you have it. Alright, so now, can we simplify this a little bit further? Sure. Let's go ahead and rewrite it so it looks a little bit better. So the first part will be 3.5 MVO minus 3, because it will be 2 times 1.5 MVO all over M. And that's going to give us our velocity final for object 1. Alright, so now that we have that, can we simplify it further? Sure we could. See, 3.5 minus 3. So it's going to go ahead and give us 0.5 MVO over M. Alright, great. And we're going to do one last step. Can we simplify it even further? Yeah, we can go ahead and get rid of the M's. So the velocity was actually 0.5 VO for the velocity final of our first object. So 0.5 VO was the final answer. In part C of problem 27, they asked, the larger block slides a distance of d before coming to rest. Determine the value of the coefficient of kinetic friction between the larger block and the surface at which it slides. Alright, so we're going to go ahead and do that. To solve for that, friction is doing work on this block to get it to stop. So work is the change in kinetic energy. So we're going to go ahead and use that as our starting point for figuring out what is the coefficient of kinetic friction for the floor or the surface with the block. Alright, so now work. How do you figure work? Work equals force times distance. Alright, so force times distance is equal to change in kinetic energy, which is final minus initial. Alright, next let's go ahead and continue. What force is acting on this block? Well, there's 3 of them. There's force of gravity, force normal, and force friction. Now force gravity and force normal, they're going to cancel each other out. So net force here is force friction. So I'm going to put a little F right there for force friction that's acting on it. How do you solve for force friction? The formula for force friction is the coefficient of, in this case, kinetic friction multiplied times force normal. So I'm going to put that, the coefficient of kinetic times force normal times d is equal to kinetic energy final minus initial. Alright, so final is actually, we're going to get rid of it. Why? At the end, it's not moving, so I'm just going to put minus kinetic initial. Alright, how do you get force normal? Force normal is equal in magnitude to mass times gravity. So we're going to go ahead and put that here. So equal in magnitude 2 mass times gravity. Alright, that's going to give us our left side of the formula. On the right side is negative 1/2 mass times velocity initial squared. Alright, so that's going to be our formula. Next, we want to go ahead and solve for the coefficient of kinetic friction in this case. Alright, but before we go any further, we should go ahead and start putting in our values. Alright, so for example, m, what's the value for m? It's really 1.5 uppercase m, because this problem said, hey, use the letters and the symbols that we gave you. Alright, so we're going to go ahead and do that. So I'm going to rewrite it with all the proper values. M, G times uppercase D they gave us. Alright, so that's going to be equals 1/2 times 1.5 uppercase M multiplied times, what was the velocity initial? Velocity initial is started at 2 meters per second. It's going to be 2 VO squared. Alright, so that would be the setup with all the proper values. Alright, so now that we've got that, we want to go ahead and isolate the coefficient. So we're going to go ahead and do that, but before we go any further, let's go ahead and multiply these a little bit, flush them out a little bit more. Alright, so it's going to be 2 squared, that's a 4, 4.5, that's a 2, 2 times 1.5, that's 3. So this is really 3 mVO squared. Alright, and this side remains the same, 1.5 mgd. Finally, I wanted the coefficient, so I'm going to go ahead and divide by 1.5 mgd. So I do that to both sides, 1.5 mgd. That cancels out. 3 divided by 1.5 is 2. Alright, so I'm going to write my final answer here. The coefficient is really 2. And notice that the m's can cancel out. VO squared over G times D. And that will be our answer for part C. Now in part D, they ask us, indicate whether the collision between the two blocks is elastic or inelastic, and justify your answer. Alright, in this case, they collided and then they went away from each other, therefore it's an elastic collision, because you can make that claim because the blocks crashed against each other and then separated away from each other. They did not stick to each other, and that's why it's elastic. Alright, that takes care of part C and D of problem 27. Up next for us, we're going to look at glancing collisions. These are collisions that happens when the objects are not a straight head-on collision. They're a little bit at an angle, and that's going to create some, well, essentially two-dimensional motion where you have an X and Y. That's more of a more common collision. Or it says when an object strikes another object off-center, it's called a glancing collision. These problems use these formulas right here. And notice it's the same formula for momentum, but they have an X's in there and Y's in there. So you're going to break it down into an X and Y component here. Now, the equations can be written for the x-axis and the y-axis as such right here. And the zeros are for all the y's, and the zeros here are for all the x's. And those are the formulas that the book uses. I go ahead and take a different approach as I do these, so I won't be using those formulas from the book solving this problem. Alright, so in example 8 it says a car with a mass of 1.5 times 10 to the 3 kilograms traveling east at a speed of 25 meters per second. So there's our car, collides with in the intersection of with a 2.5 times 10 to the 3 kilogram van, as you see it right there, traveling north at a speed of 20 meters per second. So there's a collision. There's our diagram. They're going to collide. They're going to go somewhere in that direction. Find the magnitude and direction of the velocity of the wreckage after the collision, assuming that the vehicles undergo a perfectly inelastic collision. That means that they stick to each other, so their bumpers are tangled up. And assume that friction between the vehicles on the road can be neglected. Alright, so it's the instant after the collision, which direction are they heading, and how fast are they going. Alright, so that's what we're looking at, the direction and the speed. Alright, first of all, let's go ahead and solve for the momentum of the vehicle. The vehicle, the car, we're given the following. So we're going to label that as 1, the car. So we're going to label that as M1. It has a mass of 1,500 kilograms. And it has a velocity to the right, velocity initial it's to the right of 25 meters per second. I'm going to put a positive, it's to the right. All right, and it collides with our truck. Now our truck is M2, that's what we're going to label it. It says a van actually, but the picture is a truck. All right, but the van, and it has a mass of 2,500 kilograms and is traveling northbound, so at 20 meters per second. So that's all the information that they give us. All right, so this is what we're going to do. We're going to solve for the momentum of each one of these separate, and then we're going to put them together into a diagram. All right, so momentum number one is really mass times velocity. So I'm going to multiply 1,500 times 25 gives me 37,000 kilograms times meter per second. All right, momentum of vehicle number two. All right, that's going to be 25,000 times 20. It's going to give me 50,000 kilograms times meters per second. So that's their momentum. All right, next I'm going to go ahead and draw a vector diagram. All right, so our first component is the momentum of the car, which is going to the right, 37. And next, my next vector is going to be the momentum of the truck, which is going northbound. So I'm going to have from the arrowhead here, that's going to be the tail of my arrow, is going to go 50. And I ran out of board, so I'm going to make this one a little smaller. So this is 50,000 versus this one is 37,500 kilograms times meters per second. All right, so that's what we got. Now, what do we have to do? We have to find the total momentum of these. And once we have the total momentum, we can go ahead and find the velocity of the wreckage, which is what we want. So what is the total momentum here? Well, we got their two components, so there's our vector right there. All right, now this is a right triangle, so we can go ahead and use that Pythagorean theorem to go ahead and solve for that. All right, so we're going to go ahead and use, again, Pythagorean theorem. That's A, that's B, and that's C. So A squared plus B squared equals C squared. So I'm going to go ahead and multiply 37,500 squared plus 50,000 squared equals a very large number. I'm going to square root of that, and it's going to give me 62,500 kilograms times meters per second. That is my total momentum going in that direction. All right, now for total momentum, you can use that to find the velocity. So the wreckage has a momentum going in that direction. All right, so I'm going to say my total momentum is equal to the total mass, which is really the mass of vehicle 1 plus mass of vehicle 2, and their velocity final that way. And that's how we're going to go ahead and find it. So divide, and it's going to go ahead and be the following. Velocity final is equal to 62,500 kilograms times meters per second over the addition, the mass, the total mass of both of these vehicles, which is 4,000 kilograms. So just divided by 4,000, that will give us the velocity final for this wreckage. It is 15.6 meters per second, and that is our answer for the velocity final for this wreckage. Up next, we're asked not just the velocity, but in which direction are they heading? So the angle, theta, right there, in which direction are they heading? All right, so that's what's up next for us. All right, and for this one, we can either use sine, cosine, or tangent to go to figure out. Sine is opposite over hypotenuse. Cosine is adjacent or hypotenuse, or tangent is opposite over adjacent. All right, well, let's just go with sine. It's the most common one. So sine is 50,000 over 62,500. So it's going to look like this. Sine of theta is equal to 50,000 over 62,500. All right, so I'm going to go ahead and get my calculator, plug that in. So it's going to be 50,000 divided by 62,500 gives me 0.8. So sine theta equals 0.8. Now I'm going to go do inverse sine to get the angle of 0.8. And that's going to give me the angle for this. So inverse sine of my answer is 53 degrees, 53.1 degrees. And that is my answer for the direction. So we got the magnitude, the speed at which they're traveling at, and the direction 53 above the x-axis. Alright, that takes care of example 8. In problem 28, we're asked a follow-up question. Said, if the car and the van had identical masses and identical speed, what would be the resultant angle between them? Alright, well, let's look at their vectors again. If they have the identical mass and speed, both vehicles, they would have identical momentum as well. So it'll be one arrow right here and another arrow of the same length right there. So they ask you what angle would this be? Well, these two are the same, alright, and that's a right triangle. Therefore, that angle should be 45 degrees. So the angle is 45 degrees. It's an isosceles triangle. So there's your answer. Alright, let's go ahead and move along next to problem number 29, our last problem for this video. Alright, so in problem 29, they go ahead and they ask you as the following question. It says, you have an object. This object is initially moving in the positive x direction with a velocity of 5 meters per second. So here's our object, and it's moving that direction. It has, again, a mass, we're going to call it object 1, of 3 kilograms, and a velocity initially of 5 meters per second positive. And it collides and sticks with a second object. The second object has a mass of 2 kilograms and it's initially moving in the negative y direction with a velocity of 3 meters per second. So here is our second object and moving negative y direction, and they're going to collide here. And again, the mass of our second object and velocity initial of our second object are 2 kilograms and negative 3 meters per second. Alright, so that's information that they give us. Then they ask you find the final velocity and the direction of the composite object, which is both of them put together. Alright, so we're going to go ahead and solve for the momentum of each one of these, and then we're going to do a vector diagram. So momentum, you simply multiply them. So the momentum of object 1 is mass times velocity. So this is 15 kilograms times meters per second. Momentum of object 2 is going to be 6 kilograms times meters per second, negative because it's in the negative y direction. Alright, so now let's go ahead and draw some vector diagrams. My first arrow is 15 long, so I'm going to go ahead and go roughly about that long. Its momentum is 15. Now my other arrow for the object going down, I begin my next arrow at the end of this arrow, at the arrowhead. That's going to be the beginning of my next arrow. It's going to be down, and it's going to be only 6 kilograms times meter per second in the negative y direction. So we're looking for that length of this arrow, and it is a right triangle, and that we're going to go ahead and use to figure out the velocity, and we're also going to look for the angle, the theta, but that's after. Alright, so let's begin with figuring out the length of that hypotenuse. It's a right triangle, so we're going to use Pythagorean theorem. So it's going to be a squared plus b squared equals c squared. So this is our c. We need to figure it out. So it's going to be 15 squared plus 6 squared, and then we get the square root of that value. So it's going to be 16.2. That is the momentum of the whole wreckage. Alright, so if that's our total momentum, and the total is the mass of object 1 plus mass of object 2, and that will give us our final velocity. So velocity final is going to be total momentum 16.2 divided by the total mass. This is 2, that's 3, so it's 5 kilograms. So it's going to give us our final velocity. It's going to be 3.2 meters per second. Alright, that is our final velocity of a wreckage. The direction on which they're heading. For this problem, again, we're just going to use sine, cosine, or tangent. Let's go ahead and use sine. Sine is opposite of our hypotenuse. So it's going to be sine of theta. It's equal to opposite, which is 6 kilograms. That's meters per second. Over the hypotenuse, 16 kilograms. That's meter per second. Alright, so 6 divided by 16 gives us 0.375. Next, I want just the theta, just the angle. Get rid of the sine by using inverse sine. So it's going to be inverse sine of 0.375. That's going to go ahead and give us 22 degrees even. So that will be the answer. So the velocity is 3.2 meters per second that direction, 22 degrees below the x-axis. Alright, that takes care of problem number 29. This also brings us to the end of this lesson. Thank you so much for watching.